Hello friends. So this video is about filter design. Particularly it's called as digital filter design. So commonly in digital signal processing we use filter design. Okay, that's a very common topic, filter design. Fine. So whenever I talk about filter, so first we should know what is a filter. So basically we know filter, we might have studied in basics of electronics. A filter is one which selectively passes certain frequencies. Okay, selectively pass certain frequencies and cut off other frequencies. That is called as a filter. And we also know there are different kinds of filters. We have a low pass filter, high pass filter. So low pass filter essentially passes only low frequencies. High pass filter passes high frequencies. Band pass filter, which allows a band of frequencies. For example, if you see the frequency response of a low pass filter, ideally it should be like this, and a frequency response of a high pass filter ideally looks like this, and a frequency response of a band pass filter ideally looks like this. Okay, and also we have band reject filters. So band reject filters ideally have a frequency response like this. So this is the band of frequencies that are getting rejected. This is the band of frequencies that are getting passed. These are the high frequencies that are passed in a high pass filter, and these are the frequencies that are passed in a low pass filter. Okay, so when it comes to digital design of filters, okay, so particularly for digital design of filters, we are actually bothered about two types of filters. Okay, one is an IIR filter, second one is an FIR filter. Okay, so the expansion of IIR is I stands for infinite impulse response filters. Okay, infinite impulse response filters. Similarly, FIR goes into finite impulse response filters. Okay, so as a name in things, so normally in our systems, digital systems, you call it as impulse response, h of n. Okay, when the h of n is infinite, okay, that's called as an infinite impulse response. Okay, similarly when your response is finite, you call it as finite input response filters. Okay, so but a filter, particularly a filter, if it has to be realizable, okay, so its impulse response, its impulse response h of n should be equal to 0 for n less than or equal to 0. For n less than or equal to 0, then only this particular filter can be realizable. A filter to be realizable only if h of n equal to 0 when n less than 0, which means that it should be essentially causal in nature. Okay, you cannot physically realize a non-causal filter. Okay, and another thing about this FIR and IIR is FIR is also called as non-recursive filter. Okay, non-recursive filter, whereas IR is called as recursive filter. What I mean by recursive is recursive in which present output depends on present input, past input and past output. Then it is called as recursive. So this past output, it actually accounts for a feedback in the system. Okay, it accounts for a feedback. Whenever a system has a feedback, okay, that's about the past output. Okay, So that's called recursive. Similarly, non-recursive means the present output depends on only the present input and past input. It depends on only the present and past input. Then it is called as a non-recursive type filter. Okay, fine. Now, as far as digital filter design is concerned, okay, so we'll first see some basic specifications. Okay, so that we'll take a simplest one, a low pass filter. And another reason for taking low pass filter into context is whenever we want to design any analog filter for your DSP, first we'll design a low pass filter, then we'll transform this low pass filter into a band pass or a high pass or a band reject. Okay, so that is the reason we take our complete explanation only to low pass filter. So first we'll design a low pass filter, then we'll transform into the required filters. Okay, so for a low pass filter, the frequency response looks something like this. Okay, ideally it should be like this. Ideally this is your low pass filter response, but in practically this will not be the case. There will be variations. Okay, so we can just something put like this. Your response will be something like this. Okay, so this point you call it as, this particular thing you call it as omega c. Okay, another thing that I want to represent is, in your analog domain you represent the frequency by using this symbol. In digital domain we so this is analog frequency, this is digital frequency. Okay, so this is omega c is the cutoff frequency. So normally for a filter you tell the cutoff frequency. Okay, but another two things to be noted here is this point. Okay, this point you call it as omega p, and another thing you call here as omega s. Okay, so this is pass band frequency. Omega p is pass band frequency, and omega s is stop band frequency. Okay, and omega c already I told you it is cutoff frequency. Cutoff frequency. Fine. Now this particular band, that is from omega p to omega s, okay, you call it as transition band. You call it as transition band. And from omega s, the entire region you call it as stop band. And from starting to omega p, this region is called as pass band. Okay, so transition band is the band where the actually transition takes place from the cutoff. Okay, so very important to note here is the transition band has to be as narrow as possible. The transition band should be as narrow as possible. So when it is narrow, then it is a better filter. Okay, it is a better filter. You call it as a better filter. Okay, ideally the response has to be like this, but when you design a filter you don't get ideal response, you will get some variation. So this band should be as steep as possible, it should be as narrow as possible. Okay, and another way to put this thing is, you find the slope of this transition band. If the slope of the transition band is I, if the slope of the transition band is I, it has a better rejection ratio. Rejection ratio is better, the rejection of that unwanted frequencies. Okay, so rejection ratio of unwanted frequencies is I, it is better. Okay, now these are some of the fundamental things you should note. And another thing here, okay, so I told this is passband frequency, and here you mention another term as passband attenuation, and similarly here corresponding to omega s you mentioned something called as stop band attenuation. Okay, pass band attenuation and stop band attenuation. Okay, so next we'll see about what are the essential requirements for a filter. Essential requirements for a filter. Okay, so first thing, already we have seen one criterion, h of n should be equal to 0 for n less than or equal to 0, which means that the system has to be causal. The first condition is it should be causal. Second condition, it should be stable. The system has to be stable, then only it will be able to do the required operation. Okay, third one, whenever we talk about frequency response, okay, in general whenever we talk about frequency response, two terms are there. One is a magnitude plot, second one is a phase plot. Okay, so it should have a good magnitude characteristics. Magnitude characteristics must be good. Okay, magnitude characteristics must be good. Similarly, the phase characteristics should be linear. The phase characteristics should be linear. Okay, these three things are very important. Fourth important criterion is order of the filter must be small. Order of the filter must be small. Okay, so order is a very important criterion. What happens if the order increases? If the order increases, the complexity also increases. The complexity also increases. That is why order should be less. Okay, very interestingly, say an IIR filter. Suppose in an IIR filter you have implemented a third order filter. Okay, you have implemented a third order filter to get the same response as that of an IIR filter in FIR filter. Okay, you need really a 200th order filter to get the same response as that of your IIR filter. Okay, so you should understand, normally FIR filters designing is very easy. Okay, but if you want a performance similar to third order IIR filter, you should have the 200th order FIR filter. Okay, so think about it. Okay, that's one thing we have to decide. Fine. And apart from this four criterion, there are also some more criterion are there. Okay, one thing very common is the transient response has to be good. Transient response has to be good. Okay, it should have a good transient response. Second one, it should have a steady state response. Steady state response should be in acceptable limits. Steady state response in acceptable limit. And normal things, rise time, you should have a good rise time or a fast rise time. Rise time should be fast. Rise time should be fast. And similarly, settling time must be as small as possible. Settling time should be as small as possible. Okay, these are the other criterion apart from the fundamental criterion. Okay, and one more point to be noted here is as the order increases with respect to the order, okay, this is what your ideal response, and I told you this is a practical response. A practical response looks like this. So as you increase the order, okay, it approaches the ideal response. Say this is n equal to 1, n equal to 2, n equal to 4. As the order increases, it approaches the ideal response. Okay, so in this session we have seen about what are the different types of filters basically. So we started with a basic filter design and we saw about so I'll just sum up what we have seen in this class. In this session we have seen about what is a digital filter. Okay, we have seen what is an FIR and IIR filter, what is recursive and non-recursive filters. Okay, so where the recursive and non-recursive comes, and we also seen about what are the different criterion, okay, First we have seen about the specifications. So specifications are a passband attenuation, stop band attenuation, then omega c cutoff frequency, passband frequency, and stop band frequency. Okay, and we have also seen about what are the essential requirements for a implementation of the filter. Okay, it should be causal, it should be stable, it should have a good magnitude plot, it should have a linear phase characteristics. Okay, this is what we have seen. Thank you.